Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual landscape of the late 17th century was a crucible of mathematical innovation, a fertile ground where problems of motion, change, and curvature pressed relentlessly against the established boundaries of geometry and algebra. Within this environment, the 1675 publication in the Journal Acta Eruditorum of Gottfried Wilhelm Leibniz paper, Nova Methodus pro maximis et minimis, item tangentibus, qui nec fractus nec irrationales quantitates morita, et singulare proles calculi genis, represents a moment of profound conceptual crystallization. This document, whose title announces a new method for maxima, minima, and tangents, undeterred by fractional or irrational quantities, and a singular type of calculus for them, is far more than a procedural guide. It is the public birth announcement of the differential calculus, a system of thought embodied in a notation of extraordinary power. The present analysis undertakes a systematic evaluation of the internal claims, logical structures, and unfolding arguments presented within the compact and potent sequence of Leibniz exposition, examining the work on its own terms as a self-contained engine of mathematical discovery. Section 1. The foundational claim of a universal symbolic language. Leibniz begins by defining his terms and his calculus. He posits that a line segment, designated by a letter like x, has a corresponding infinitesimal change, which he denotes as dx, the differential of x. This initial claim is deceptively simple, yet it contains the seed of the entire system's power. The assertion is that this operation, the staking of a differential, is a universal one, applicable to any variable quantity. He immediately provides a foundational rule: the differential of a constant is zero. This elegantly captures the idea that static quantities experience no change. The core claim here is the creation of a symbolic operator, d, whose consistent application to variables and their combinations can reveal geometric truths. The notation itself is an argument for universality. Unlike previous methods, which were often bespoke for specific classes of curves, Leibniz's x or die suggests a general process, an algebraic routine that can be applied to any equation relating variables, thereby promising a unified approach to a vast range of previously disconnected problems. The very form of his symbolism carries the weight of his ambition for a characteristica universalis, a universal language for reasoning. Section 2. The operational rules of the new calculus. Following the introduction of his notation, Leibniz presents the core operational rules of his new calculus. He states the rule for sums and differences, that the differential of x plus y minus z is equal to the differential of x plus the differential of y minus the differential of z. He then offers, without extensive geometric derivation, the pivotal product rule. The differential of the product x times v, he claims, is equal to x multiplied by the differential of v, added to v multiplied by the differential of x. This is followed by the quotient rule, presented as a consequence of the product rule. Finally, he provides the power rule for integral and, by implication, fractional exponents. The central claim of this section is that this small set of algebraic rules is sufficient to find the differential of any algebraic function. The evaluation of this claim hinges on their efficacy. Leibniz presents them almost as axioms of a new symbolic game. Their justification within the paper is purely operational. Their truth is demonstrated by their utility in the sections that follow. He constructs a magnificent analytical edifice upon a foundation of infinitesimals whose rigorous definition remains decades in the future. The coherence of his system is internal. Once these rules are granted, the subsequent results follow with algebraic certainty, a testament to the power of a well-designed algorithm to bypass complex geometric reasoning. Section 3. A general method for determining tangents. Leibniz immediately applies his new machinery to the classical problem of finding the tangent to a curve. He considers a curve defined by an equation relating an abscissa, x, and an ordinate, y. The claim is that his method provides a direct and general solution. He asserts that the ratio of the differential of y to the differential of x is equal to the ratio of the ordinate y to the length of the subtangent. The subtangent is the segment on this axis between the foot of the ordinate and the point where the tangent line intersects the axis. By finding the differential of the curve's equation using his rules, he produces an equation involving x, y, dx, and die. From this, he can algebraically solve for the ratio die divided by dx and, by setting it equal to y divided by the subtangent, solve for the length of the subtangent. This determines the tangent line. The evaluation of this section's claim reveals its brilliance. It successfully transmutes a fundamentally geometric question into a purely mechanical, algebraic procedure. The genius is in the framing. The tangent is conceived as a line passing through 2 points on the curve that are infinitesimally close, and the ratio of the infinitesimal sides of the resulting triangle, die and dx, defines its slope. The method's claim to generality is strong. It works for any curve whose equation can be written and differentiated, elegantly sidestepping the intricate geometric constructions required by his predecessor. Section 4. The core principle for Maxima and Minima. Here, Leibniz arrives at the titular subject of his paper. The central, revolutionary claim is that for a quantity, y, to attain a maximum or minimum value, its differential, die, must be equal to 0. He argues that at a highest or lowest point, the curve is momentarily flat. Its ordinate is neither increasing nor decreasing. In the language of his new calculus, a state of non-change is represented by a zero differential. This insight, connecting a key geometric feature to a simple algebraic condition, is the heart of the paper. Its evaluation reveals a profound leap in abstraction. Where others saw a geometric peak, Leibniz saw an algebraic singularity, a point where the rate of change vanishes. This transforms the search for extrema from a visual or geometric puzzle into a straightforward calculation. Differentiate the function, set the resulting expression equal to 0, and solve for the variable. He further qualifies the claim by stating that die can also be infinite, a subtle but crucial addition that accounts for cusps where a tangent becomes vertical. While less developed, this part of the claim demonstrates an awareness of more complex curve behaviors, reinforcing the method's robustness and scope. This principle represents a paradigm of analytical thinking, reducing a complex qualitative search to a standardized, quantitative procedure. Section 5. Higher order differentials and the nature of concavity. Leibniz method unfolds with recursive power as he introduces the concept of second differentials. He denotes the differential of a differential, such as ddx or ddy, with the notation ddv. The central claim of this section is that the sign of this second differential determines the nature of the extremum and the concavity of the curve. He proposes that if the value of die is increasing, the curve is concave up, and if die is decreasing, it is concave down. A positive second differential, ddy, signifies an increasing differential corresponding to a minimum value. A negative second differential signifies a decreasing differential corresponding to a maximum. This is an extraordinarily sophisticated claim for its time. It shows that his calculus is more than a tool for finding tangents and extrema. It is a system for describing the deeper geometric character of a curve. The evaluation of this claim must recognize its pioneering nature. Leibniz is providing an analytical test for concavity, a property previously assessed through visual inspection or cumbersome geometric arguments. The ability of his D operator to be applied iteratively, each application revealing a new layer of geometric information, is a powerful demonstration of the calculus' internal coherence and generative capacity. He is building the true theory of local curve behavior, all from his initial symbolic postulate. Section 6. The method's extension to points of inflection. Building directly upon the logic of the previous section, Leibniz addresses the problem of finding points of inflection. These are points where the curvature of a curve changes direction, from concave up to concave down, or the reverse, The claim here is a direct and elegant consequence of his analysis of concavity. A point of inflection occurs at a place where the second differential, TDY, is equal to 0. This is the point where the growth of the first differential, die, itself ceases to grow or shrink, marking the transition. The evaluation of this claim confirms the comprehensive power of his system. In just a few short paragraphs, he has provided a unified algebraic method to locate three critical features of any curve: its tangent at any point, its maximal and minimal values, and its points of inflection. The location of inflection points through the vanishing of the second differential was a particularly difficult problem for earlier geometers. For Leibniz calculus, it becomes a natural, almost effortless, consequence of the system's own rules. This section serves as a capstone to his initial program, demonstrating that his method is a complete toolkit for the local analysis of curves, all functioning through the mechanical application of a few simple rules of differentiation. Section 7, the final assertion of transcendental power and universality. In his concluding remarks, Leibniz makes his boldest claim. He asserts that his method is completely general and is not impeded by the presence of fractional or irrational quantities in the equations of curves. More significantly, he declares its applicability to what he calls transcendental curves. These are curves, like the cycloid or the logarithmic curve, which cannot be expressed by a finite polynomial equation. Such curves were notoriously difficult, often impossible, to handle with the existing methods of algebraic geometry developed by Descartes and his followers. The claim is that the differential calculus transcends algebra. By treating quantities and their infinitesimal changes directly, his method can operate on relationships that escape finite algebraic description. Evaluating this claim highlights the true revolution Leibniz initiated. He was aware that he had created something more powerful than a clever extension of algebra. He had created a new branch of mathematics, an analysis of the infinite, capable of modelling a far wider universe of physical and geometric phenomena. This final claim of universality, particularly regarding transcendental curves, was the feature that most distinguished his calculus and secured its ultimate triumph as an instrument of science and mathematics, a true singular type of calculus for the modern. In conclusion, a close internal evaluation of Leibniz 1675 Nova Methodus reveals a work of extraordinary logical cohesion and intellectual audacity. Each section builds systematically upon the claims of the last, from the introduction of a universal notation to the axiomatic presentation of operational rules and onward through their application to tangents, extrema, concavity and inflection points. The claims made within the paper, while resting on the philosophically uncertain ground of infinitesimals, are operationally sound and demonstrate a profound internal consistency. The genius of the work lies less in the rigorous proof of its foundational elements and more in the creation of a powerful, self-contained symbolic engine that, once set in motion, generates profound geometric insights with unprecedented ease and generality. It stands as a masterclass in the power of notation to structure thought and as the definitive announcement that a new era of mathematical analysis had begun, one capable of taming the continuous and the infinite through the elegant manipulation of symbols. The paper's enduring significance is rooted in its demonstration that a well-conceived calculus could serve as a universal instrument of discovery, a promise it so brilliantly and lastingly fulfilled.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.